Yeah, it says here request permission.
What?
It says here request permission from host for a meeting from meeting host.
Yeah, but I'm so far I'm not getting an error message on the recording, so I'm thinking that it might actually work from my side.
Yeah, it's
Uh,
recording. It shows that you're recording.
okay, then that should be okay. Then I'll just go ahead and post it like have been doing.
Okay.
You'll have to remind me what page we left off on. Oh yeah, let's see what else. There should be some tools if I can find them here. Oh, there they are. Okay, let's see one of those tools. One of them would be like almost like a laser pointer, if I remember correctly.
I
Spotlight
think
up.
if you go in the slide, oh well, there you go. You have it.
I think that's it. Okay, so let's see. I think as long as I can control it with the. Okay, so what page was I on? Oops, whoops, interesting. Let's see, page. How come I can't go to the next? I have to turn that off to go to the next page. Maybe I do. Weird. Okay. Oh no, okay, that's okay. What page was I on? I think we finished the all cases except for the parabola, right? Yeah. We did the ramp, right? I thought we did the ramp. And so in this type analysis, I'll just maybe go back a minute to the table real quick. It's sort of a good summary for where we are. It's got most of the information we need. I think there's a table in here. Let's go forward here. That's the table. Okay. So what we had before was we knocked out the first two rows. And there are two important parameters that go with the analysis in this section. One would be called the type, which is given the symbol capital N. And the other one is this symbol M, which identifies the type of input. So for example, for a step, M is equal to 1. A ramp, M is equal to 2, and for the parabola, M is equal to 3. And we saw that, in fact, that at least when we did the first two columns, that as the type number went up, the ability to track better improved. Okay, so you get better tracking with higher N. As we saw in the first case, we actually, our first column, when I say first case, the first column would be for the step. And then we had the different types here. So we saw that we got a finite error when the type number was 0 for a step. And that would, we discovered that would be in agreement with this rule, which would identify those cases on the diagonal where the finite error occurred. When the N was greater than that number, which we saw two cases of in the first column, then the steady state error was 0. When we progressed and look at the case for the ramp, of course the ramp has M equal to 2, so where we get the steady state error is N equal to 1. And then when N was less than that, we got basically the steady state error was not bounded and least attractive situation. And then when N was equal to 2, 2 would be greater than 2 minus 1. Therefore, it turns out that was the type number was big enough to guarantee that we had a 0. We didn't really do the parabola case, so I think that kind of summarizes where we left off. Any questions I can answer before we go on to the last case, the parabola? Okay, I'm not hearing any questions. Hopefully you'll let me know if you got one. Oh yeah, okay, so here is the parabolic case. Started here. As before, we could spin this formula off from the Swiss knife formula having arbitrary n and m, which was, I guess, according to my notes here, page 12. And there's that page, that formula 12, which had both the n and the m in it. And I think for the parabola, we would proceed to set the m equal to, anybody out there? What am I going to set it equal to?
3.
3, correct. So I'm going to put 3 in for the m, just to keep that in mind when we look at this for the parabola case. I'm going to put 3 in, and so minus 3 plus 1 is a minus 2. And so that was the part of that exponent with the minus m plus 1, so that basically where you got the minus 2. And the rest of it just repeated, denominator part. So we're not surprised when because we would say, okay, one thing we could ask first is when we might expect a finite error, because it is sort of the line of demarcation, between the cases where we have the infinite error and the zero steady state error. So we would say, well, when does n equal m minus 1? Well, since m is 3, that was when the n is equal to, I believe, let's see, 2. So we expected 2 cases for n equal to 0 and n equal to 1, since they're both less than n equal to 2, meaning the system is not able to track as well as it could, let's say, for the n equal to 2. So therefore, and the n equal to 2 was the finite error case, which we'll see in detail. So those would be infinite errors. And if you go back and check and plug in, you'll see that's correct. Did I do that too fast? Speak up if that's the case. Okay. Should I go faster? I don't know. All right, so then we can proceed to take a look at the case when the n is equal to 2 to come up with a recipe for the finite error. And all we need to do is then go back up the top here and set the n equal to 2, since the s to 0 is 1 and the n2 there. Taking a limit knocks out the first term in the denominator, but leaves the second one there, still there, of course, just because we already set the s equal to 0 a long time ago. And we get this ratio. And somewhat consistently, since we had the first one with the step, we had the position with the ramp, we had the velocity constant. Now we have this acceleration constant, which is associated with the parabola. Okay, and that constant is what we see here. So we repeat the argument again that the convenient way to evaluate that constant would be not to apply this formula literally to go after the zeros and the poles, but pretty much take this sort of sidestep, which actually works out to get you answer faster. And then it would be to observe that, and this, I guess, I go back to equation 7, what we had. If we go back to equation 7 and set n equal to 2, we see, in fact, that we get this, what we see here. Okay, and so we can, go back real quick to equation 7. Should be on this page. Right, there it is. So we just take that n and set to 2, and we'll go back now to the page we're on. I think this page we're on. So we set the n equal to 2, and that's how we got that formula. And then we would observe that we can multiply through by both sides by s squared without doing anything wrong. And that would give us what we see here. And we see, in fact, once you do that, then in the limit that s goes to 0, you simply get, setting the s's there equal to 1, you get this quantity. So, basically now the s squared's on that side, taking the limit means all you have to do, the only place the s's appear now are in that numerator and denominator appearing one place, set them both to 0, and then you get this. Then somewhat happily, we see that in fact that's exactly what we need up here. And I'm sure it's not a coincidence, but let's just say we're happy to see it happen. And then we say, oh, we can get that acceleration constant by just following this limit process we have here. All right, there are no questions. I'll go to the next page here. All right, so we've seen that for the case of n equal to 1 and the n equal to 0, no sense in drawing a picture. We've just argued that the steady state would blow up. But if we looked at the case, what would it mean if we had for the parabola input, we had a n equal 2 system, then we might expect a picture like this, where yes, we see a finite error. And that value would be predicted according to that recipe. And if we take a look, we see that in fact it's absolutely in agreement with the table that we have from the book, which is right there. Okay. So I think this kind of summarizes some of the ideas. I think this part right here is intended to cover 3 cases for the whole table, pretty much. So in a sense, here we finish, I think, the parabola, and here we're just talking about just some general results that we could write down that would be helpful to us as a summary. Always a good thing to do, I think. Okay, so as a summary, some of the takeaways, I think, from the discussion that would be helpful in problem solving was we saw that there was we saw a pattern here that we got the finite error cases when the type was equal to m-1, and that was been the diagonal on the table. And we saw that if the type was greater than m-1, then that meant the system was actually in a better position to deal with the tracking problem and gave you 0. And if the n was less than n-1, then it was not up to this task, and it gave the error, steady state error was infinity. Let's see, yeah. Then we saw that, we got to find, the only time that we needed these constants was on the diagonal of that table. And I think we matched these up correctly. If you check in all 3 cases, n is equal to m-1. That'd be on the diagonal. And for each one of those diagonals, we see there's a place for Kp, Kv, and Ka. And here is our so-called preferred way to get those constants to plug in. And, just in brief, we could argue that we found that in all 3 cases, Kp, Kv, position, velocity, acceleration, they all turned out to be this particular ratio each time. And it just, turned out that way. But using this is writing it down was just reminding us that, well, they had that common property, but in reality, it's not suggesting that's the best way to do it. This is the best way recommended to do it. Also, one other point is we may want to remember that the z's and the p's that are showing up here really are not the actual zeros and poles, because there's a minus sign we would want to put in there if we want to be precise, and we usually like to be precise as possible. All right, so I think that wraps up the, everything we would need to look at an example. Anybody have any questions about the anything so far? I'm gonna go to the next page. So we got an example. Seems like at least we should do one example. Okay, so I believe this is the same example as in the book. And we're given a problem, I guess, example 5.3. And we see this as a figure that goes with that example. And consistent with the constraint that we have in the section we're talking about, this is a unity feedback system. We have a controller block and a so-called vehicle dynamics block, sometimes called plant block. I don't know if we call it the plant. The second block is fully specified throughout the problem, okay, as following this rule with a K in it. Oh, this is where I'd like to do a zoom if I could, but can you read that the GC is, even my vision is not great unless I bring my head up there close. This is where I would benefit from a zoom. If you read it, I believe it's K1, subscript 1, plus K2 over S. Maybe you can read it better than I can. If I put this on, let's go, let me see. Let me go back to, maybe it'd be clearer if I went back to the other method here. Let's try that. Okay. That might be a little easier to read if I can keep my pointer. Oops, went too fast, all right. Okay, we're there. Is that better?
Yes. That's the same.
It's the same, okay. Well, it's a little better for me. I can read the subscripts a little better now. This is where I missed the document camera, because with the document camera I can do a nice zoom on that. I don't see a zoom feature on there. Anyway, I'll look at it. Maybe there is a zoom, or maybe I can, I don't know if I'll get the document. It will go back to campus or not right away, so we'll see. Anyway, so the so-called controller block is defined in such a way, it's a little arbitrary, as we'll see. Called K1 plus K2 over S. And you would, if in the language of control theory, the K1 would be the proportional part, and the 1 over K2 over S would be the so-called integral controller part. Now, in the first part, there's two parts, as some problems have. In the first part, part A, we're told to take the K2 to be 0. Okay, just say, okay, we're going to turn off the integral part of the controller. And then proceed to answer the questions. Okay, so once we take the K2 to be 0, of course, that simplifies it somewhat because that term's not there. And as you know, part of the recipe is to do the product of the G times GC, which we can do right here. And there's your G, and then the GC is just simply the constant K1, which now is there. Now, for purposes that may or may not be necessary, but certainly is not incorrect, we can write it this way. Okay, and maybe that's just to clarify that we don't really have I mean, I would say it's true back here, but it's also, it would drive home the point, there is a pole, but it's not at S equal to 0. Okay, it would be S equal to a minus 1 over tau. So since it's you would say, well, there's no pole at S equal to 0. That's like saying S to the 0, the superscript 0, back in the general form. Let me see, I don't know if I can go back real quick here and show you that. I don't know how far back I gotta go to, let's see. Right. So yeah, so you see when n is 0, if there is no pole at s equal to 0, then you'd say that n is 0, right? So that's where we could say that's a type 0 system. Okay. All right. Now we're told, okay, this is just given to us. We're told to consider a step input. I guess that would be step with amplitude A. Okay, so then with m equal to 1, I mean, because the step is m is equal to 1. And we see that that's exactly the right condition for a finite error, right? Because then you say, well, if m is equal to 1, 1 minus 1 is 0, but this is a type 0 system. So we met the condition for finite error. So we're not surprised we need one of those rules. And if you wanted to, you could say, well, a backup on this would be, let's take a look at the table, which you'd have, in problem solving. A good reference for problem solving is that table. Yeah, there it is right there. So we're a type 0 system, step input, and then, so there we are. And we can also then use the summary of the information on the previous page, which would be, okay, we saw that we need that case of P, so we'll use that recipe to get the case of P. And yes, we see that that's consistent with the information we have for the system for step input type 0 system. So yes, I'll pull up the same recipe and just setting the S equal, let's see, so where are we on this? Yeah. So we look at the GCG, and we see the GCG for this particular case, part A, is this. So all we have to do is then set S equal to 0. And we see that we set S equal to 0 since that the 1 over the time constants in the denominator, but we have a 1 over time constant in the numerator. We can predict confidently that those are going to go away. And we're just going to end up with the K1 times K. Right. Now you got to be careful because in for the step case with the n equal to 0, of course, when you have the finite error, the form is a little different because you got the 1 plus the constant, where the other two columns for the ramp and the parabola, it's a different form. But that's why we got the table to remind us of that. So anyway, yeah. So our KP needs to go in just as we see it right there. Which we see the form is a little different. Here we got to add the 1 before we do the division, and here we don't for the ramp and the parabola. So this is the conclusion from the problem was, well, this is putting our KP in, this is the end result. And yes, the answer is symbolic, but presumably, let's say someone gave you the K1, the K, and the A, it would just be a plug-in after that. So it's considered that's like the completion of the part A of the problem. Any questions on that? Okay, well, no, actually part A does have, it's completion of the part A as far as the step input goes. If we had a ramp or if we had a parabola, then you can look at it this way. Because a ramp and a parabola are faster changing input signals, the stress on the signal to continue the tracking is higher. And so, yes, we fully expect that since the no longer is the n equal to m-1, but in fact for the ramp and the parabola, the n will be less than m-1, and surprise, surprise, those errors will be infinite. Okay, now that does finish part A. Oh, should I go to part B? Anybody out there hearing me? Should I go to part B?
You can go to part 2.
Yes.
Okay. Yeah, is there a question? Somebody have a question?
No.
No, okay. All right, now in part B, we take the constant K2 to not be 0. Okay, so we include it in our analysis. And so in that case, we're multiplying the general form, the full general form of the controller G, times the call the plant or vehicle dynamics G, so which is right there. Okay, we'll do the same trick we did before. We'll rewrite the second transfer function associated with the second block by dividing by 1 over tau, time constant, both top and bottom. And when you do that, you can say, okay, let's see, that could be written just that way. I mean, of course, I just switched the order here a little bit, but it's really all multiplication anyway, so hopefully it won't bother you. So let's see. I don't know. Okay, so yeah, so we can pull out the K1, the K1 from here. All this now going on in the numerator. Pull out the K1. So now we get simply an S plus K2 over K1. Now, the idea is, can you see what type system this is based on that result? Yes, a type n equal to 1, right? Because that S to the first power. The other places that you do see an S in the denominator for a pole are not a pole at 0. So that doesn't prevent us. So the important thing is, well, yes, that 1 over S says it does have a single pole at the origin. And we recognize that as an n equal to 1 system. All right, go to the next page here. All right, let's see. This is where I had a problem with this darn thing. I remember thinking, why do I can't, let's see if I can get rid of that. I'll go back here. Let's try. Let me see if I can close that out. Oh, yes, good. I can do that. All right, so from that result, which I'm showing here, from that result, you get this here at the top. And we know then the condition which will lead to a finite error in this case would be, since n equal to n-1 is the finite error condition, would be m equal, since we have a type 1 system, we're kind of thinking backwards. Well, what m will give us 1 on the left? And that would, of course, be m equal to 2, and that corresponds to a ramp. And that's where we get. So we see that the ramp case is the finite error case. And we can just immediately go to some of the fast and cheap answers you can get without much effort, and that'd be the one when n is greater than n-1, and the other case when n is less than n-1. So we would say, okay, when n is greater than n-1, we get, okay, that would correspond to the, so we have m equal to 2. Okay, we're doing, okay, let me just see, we have an n equal to 1. So for m greater than n-1 would be 2, And that would mean then the error would be 0, right? Because then n is greater than 1, and that's where you get the condition for the steady state error being 0. Then the other flip of this, if we so if we're taking n equal to 1, then we would say, well, what condition of m is greater than m minus 1, and that would be m equal to 3. 3 minus 1 is 2, and so 1 is less than 2, therefore it's type 1 system. Therefore, it's not able to keep up on the tracking, and therefore the error will be infinite. Hopefully I didn't confuse you on that. Anyway, any questions on that? All right. I think what I said was correct, though. Okay, so now, so what is left here, we consider the step. Okay, that means that things aren't changing so fast that the system can't give us 0 error, and it does, which is good. And then the parabola, which things are changing really fast, and yes, we get an infinite steady state error. And we already know that we expect that for the ramp, it's just right to get the finite error. So we have to look at that more carefully. Okay, so if we know that the ramp corresponds to m equal to 2, and so we go back here and look at both our table and our recipe real quick, just to make sure we're on the right track. Okay, so we see our recipe is A over K sub A. Okay, so we're working with that one. That's for the parabola. Oops, sorry. What is our, oh, we're doing a ramp. Sorry, we're doing a ramp. So here it is, A over K sub V. And for the ramp case, we needed the velocity constant, which means we have to use that recipe for getting it. And I'll remind you that velocity constant means we have to throw in a factor of S before we take the limit when we multiply the GC times G. Now the good news is we have the GCG right up here at the top, so we can see what happens. The S's will cancel before we take that limit, and then all we then have to do is set the S equal to 0 in the numerator in that one place, and in the denominator in that one place, and then you get this. And so if we, again, do a little simplification because the time constants are just the right place to cancel, our end result shows that our velocity constant in this case would come out to be K times K2. And having referred to the table already, we realize the form doesn't require us to include the unity factor in the denominator like we did for the step input. So we would just simply have A over K, K2, and that completes, I think, the problem. Any questions on that? Not hearing any questions at all on this. Should I just go ahead and start the next section?
Yes.
Okay, I'll start the next section. To start the next section, I need to pull up the other, let me get out of this. I think I need to pull up a different PowerPoint. I'm gonna close that one out. I don't think I need it anymore. Oh, let me see, let's try this. Can most of you see this, or all of you see this? Hello?
We see your background right now.
Okay, let's see if I can do it. So you can't see the slide, right?
No, we cannot.
Okay,
No,
so
sir.
then I need to, so let's see back up here then. I'm not sure why you can't see the slide. Let's see what's going on here. Any difference?
There it is.
Yes.
Okay, so it's now different. Okay, you can see my my slides, right? All of them actually from this section. Okay. So let me make it a little bigger. Okay. So it was indicated in the beginning that we would look at just look at a few cases at least where the situation was it was non-unity feedback. Okay, so we actually had two short ways to do this. Not exactly 100% comprehensive, although he does hint at it in the book. We're not going to go down. We're not going to go down that full path. We're going to just look at two methods, which are, I think, helpful. So the other two methods, the first method is where we would have, let's say, a block in there, which would be the K2 wouldn't necessarily be 1. If it was 1, then we would have a unity feedback. But it also has a block in front. Now, to put this in context, this is actually quite practical in many ways from the viewpoint of certain systems where you would have some sort of sensor where the feedback block is actually a sensor, and being a sensor, like a tachometer, for example, it could actually then convert speed to volts. Okay, some kind of speed to a volt, to a electrical signal like volts. So we see that in this block, we see it on the far left, on the input side, someone's turning a dial to set the desired speed in rotation speed, I believe, in radians per second, and that would be the R of S. And on the output, there's some result which we would call the response, given the symbol Y of S, and that's also in radians per second. So that's good. So we can basically say, well, that our error should be the difference between these. But we also recognize that maybe our processes in here would involve volts. So we have this sensor that converts the speed to a voltage signal. And so in a way, you sort of not to have try to do a comparison between apples and oranges. You want the same units you're doing this comparison with to create your activation error signal. So the point is you need a sensor more or less on the front to convert it to volts. So you compare volts with volts. I mean, hopefully this makes some sense. And in this situation, then the K2 is certainly representing some constant which would convert a certain number of radians per second to a certain number of volts, and we certainly don't expect it to be unity in general. So this would be let's say the kind of the context where a situation like this would be quite practical. Any questions on that? Okay, so then the issue is, well, can this be re-represented in a way that will allow us to do our type analysis with it? And of course the answer is yes, or we wouldn't be on this page. So let's go to the next page and see what the story is behind that. Now, as the book points out, we don't have to be fully restrained on our sensor, in the sense that here we show K2 is just a constant, which may be the case, and maybe that's you don't really worry about how the frequency responds to your sensor. Okay, and there's nothing wrong with that. But let's say, for example, you did have a sensor which you wanted to take some properties into account, like its capabilities fall off at very high frequencies, acting more or less like a low pass filter. So as long as since we know that in doing the steady state error analysis, we have to set the S equal to 0, all we really care about would be, for the purpose of what we're interested in, would be that we could say, well, that if you set the S, if you took the limit S going to 0 of the sensor feedback transfer function, if it comes up to be a constant K2, we're good to go in the method we're going to talk about. Okay, so that you could argue that we can have a little more generality to this problem, and I think in the example this is helpful. One of the examples that comes up that we need to use that. Any question on that so far? So we're more or less we're back to the same figure. Okay, so we're saying under these conditions that we have this situation, we can have it. You call it a frequency dependent sensor, but it has to meet that condition. And then once it does, we can argue then that we're back to the original diagram with a K2, simply a constant. Because really that's what we're interested in, is the DC performance here, because that's our steady state. We take the limit S going to 0. Okay, so where we're going with this is making use of some of the ideas from the past to the block diagram analysis. So what we're thinking about is, well, can we jump our connection here? I don't know, let's put it this way. What we're trying to do is, well, actually, yeah, we're trying to move this connection so it's on this side. So you could say, well, in the end, we're going to end up with that transfer function on this side of that summing point. So so just to remind you of one of our block diagram rules, I guess would be number 5. We went back and looked at the table. One of our block diagram rules would be, if we wanted to move the X2 connection in front of the G, we could do that, but in doing that, we would have to put in a 1 over G to more or less compensate for the fact that that part of the signal now goes through the G in the second version, right? So in other words, we move it here. In going forward, then that part X2 is going to be forced to go through the G, but to compensate for that, we'll put a 1 over G in there to compensate for that. And that goes back to one of our rules. Okay, any questions on that? So we're going to end up using that helpful. It's going to be helpful here. Because then we can say, well, let's move that summing point here. All right. But to do that, what'll happen is this K1 will add up to the right of the summing node, okay, just like it did here. And to be consistent, you'll have to put in the 1 over K1 in that loop, in that path leading up to that summing node right here. So just like that 1 over G, well, here this G in this summing or this block diagram rule was actually our K1 here. So that becomes a 1 over K1. Any question on that? Well, as you might guess already, it makes sense if we want to use our unity feedback analysis, it would make sense to let our K1 be equal to K2, and then that way this just becomes unity feedback. And from a certain viewpoint, that kind of makes sense. I mean, we're using the same sensor here as in a way we're using here. So same translations from radians per second to volts. And I think from a practical viewpoint, you would say, well, that only makes sense that you would want to do that. And so, any questions? So yeah, so we see, in fact, units, radians per second there, radians per second there. So we got this one sensor that converts it to volts that's in the feed forward path, and that's it. And we have unity feedback there. And so this basically one would argue this is one way that'll, once this is done, we can say, well, we're back on home plate again, so to speak. And we could argue, well, then everything we did before, we can still apply concept-wise and formula-wise. All we have to do, instead of using the GCG, we'll include this extra factor of K1, but other than that, it's all the same set of rules and ideas. All right, here's that question that I mentioned to you. Okay, before I jump in, any questions on this topic so far? So now that we're done with the ideas, we're gonna cover this example. All right. Okay, this example is from the book, example 5-4. It's based on figure 521. Let's see, I think it's one of those. There's it, 521. There's 521 there. And we're told that in this problem, the feedback transfer function is given as shown. We're told the controller G is 40 and the so-called plant G is 1 over S plus 5. And so the question is to find the steady state error for the unit step input, which we know that would correspond to m equal to 1. And since it's unit step, we'll take a equal to 1. We can check that it meets our condition for applying these ideas, because what condition was that? Well, the condition was, if we go back, was right here. In order to apply those ideas, we'd have to come up with this K2, which would be obtained by taking the limit at S going to 0. And then we would just, from then on, all we would need is that K2. So yeah, we see if we take the limit at S going to 0 for the H of S, then that's 20 over 10, which is 2. Okay, so we can take our K2 to be 2, and according to our rules that we had before, we would say, okay, according to our rules, we're going to take our K1 and K2 to be the same, so then our K1 is also equal to 2. All right, and so the process of coming up with a steady state error, then all we would need to do is remind ourselves that the situation is very similar to before, almost identical. The only thing is we want to use the extra factor of K in the recipes that we had for the for this product GCG, but now we include the K2 in there, call it GC prime. So if we do that, let's go back here. So we see we have the GC is 40 over S, and then over S plus 5, so you get the GCG. But with the extra factor of 2, it converts to 40 to an 80. I realize there's not a lot of in-between detail there, but if you followed that, or did not follow that, speak up. Or is that clear where the 80 came from? It was the 2 times the, let's see here. And you take the 40 times 2 is 80. And there's the S plus 5. So this has now given us the GC prime G, which includes the K factor. And then all we have to do is remind ourselves, well, this is the step case we're working with, and specifically the unit step, we're taking A equal to 1. So if we check our formulas that we would have, oops, I forgot those are on the previous page, yeah. Let me go forward. I think I put an equation sheet at the back here that which has the important ideas on it summarized. Okay, so yeah, so basically for the position constant, we would normally just, and here's our table down here. We're in this first column. Hope you can see that. Can't do a zoom, unfortunately. GC prime is K2 times the GC, and so basically it cyclically comes out to the whole product GCG. So K2 GCG we worked out. So that becomes our quantity that we need there, and as you can see up here at the top, that takes the place of that. So we'll get that constant Kp, and then we'll put it into this recipe with, of course, for our case, A is 1, and get that steady state error. I think that's the page we're on. Okay, so our Kp then would be just setting the S equal to 0, 80 over 5, I believe is 16, check my arithmetic. And then we put that 16 into the recipe for the steady state error. Remember, that's the first column. And you get 17. Again, you can check my arithmetic. And that's how we get the 5.9% steady state error. Now, we know already that when we looked at this system, this was a type, is anywhere on here? I thought it was on here somewhere. But yeah, type n equal to 0 system. So we know that for the type 1 and type 2 systems, which means that the type is higher, we would expect that the higher the type, the more capable it is for tracking. So it's no surprise that the ramp and the parabola should have what? Steady state error. I said predictable here, but what is it?
0.
0. Correct. It's 0. I don't know why I ever didn't write down 0. Anyway, yeah, if you look at the table, it's 0. It's the two bottom rows on that first column. It's zeros. Okay. Any questions on that? Okay. The book provides us a short and sweet second method in situations where we may not have an adjustable block in front, and and essentially, we sort of have a representation of what can happen with this one right here. So we don't have any adjustable block in front. Now, this method, you know, is not comprehensive in terms of the situations that it covers by any means, but it at least is another method which, you know, it doesn't fall within the camp of the first method because there's no required adjustable block up here. So it's fairly direct, as you'll see. It really doesn't require the heavy-handed type analysis we just went through. It sort of goes around it in a way, but it's okay. But the only thing is, one of the big limitations for this method would be it is strictly speaking only for step inputs. And so that would exclude the ramp and the parabola. And so, and it doesn't really, what's the word, require a specific type analysis. It just follows what we already know in terms of the final value theorem methods. And as you'll see in the example, it works fine. So it can work. So how are we doing on time here? Okay, you got it sometime. Okay, so our error, you know, I just remind you, our so-called tracking error was defined as our input minus our output, and our transfer function would be the times our input is our output. And so again, if we simplify this by plugging it in, and here I'm going back to basics because our intention is not going down the same path as getting to a type analysis. So it's sort of, we're kind of going back to ground zero, but it's okay. And so we can write an error here as the error, the error in terms of the input signal and 1 minus the transfer function, right? So you notice you can factor out that input R of S and write it as 1 minus T of S. So the steady state error, then it becomes the limit. By definition, it's the limit that t goes to infinity, but according to the final value theorem, you take the e of s multiplied by s and take the limit that s goes to 0. Okay.
Oh, why wouldn't the error be the output minus the input?
I'm thinking we did this consistent with what we did before. And your question is not a bad one. It's just that I'm thinking I'm consistent with the convention that we have to use to be consistent with the book. But let's do this. Let's check our formula sheet here real quick. I believe it's on there. Oops. Okay, there it is at the top. Let me see if we can get rid of this. I can. Okay, there we go. It's hard to. I think you can see it up there. I think if you go back to the starting point with the type analysis, we use the same convention. So if you want to say, well, why not making output minus input? I think we're just being consistent with the convention that's commonly chosen. And to give credit to your question, I don't see anything magic about the order here other than we want to be consistent with what other people are doing in terms of how they define the error. That's all. Is that my answer your question or not?
Yeah.
Okay. I mean, that's a good question. I mean, why didn't they define it that way? Well, somebody decided that's the best way to define it. And so everyone followed suit after that. Go too far here. Okay, so yeah, so then we applied the final value theorem, and that's it right there. So in applying the final value theorem, I'll remind you, because we limit our discussion to step inputs, then we have the a over s. We put that in, the s's cancel, set the s to 0 in the transfer function, and we get this simple recipe for the steady state error in terms of the transfer function for the system. Okay, and here's the problem example of the second. How much time I got left? Is it minutes? What is it? How much?
2 minutes.
2 minutes. I tell you what, I'll pick this up next time. If you have a chance to read this over in advance, I don't think I'm not going to get far enough in 2 minutes. I'll pick it up on what is it, Wednesday.
So can you put your pointer down there at the bottom?
Put my point.
Your pointer down there at the bottom left of the slide.
The bottom left?
Yeah. Do you see move your pointer again? Look at the bottom left of the page. Do you see where it has like the magnifying glass?
Oh yeah.
I think that might be your zoom.
Oh, okay. No, I didn't. Thank you for that. We could try it right now if you want. Would I just click on it? Let's see what happens. Oh, that's nice. Okay, well that answered that question. Now how do I reverse it? Let me see. Just click again, maybe. No, it didn't do it. How do I reverse this?
I don't know. Maybe put your pointer back over there at the bottom left again. I don't know.
I can't seem to get it reversed now.
If you have a scroll, maybe you can scroll out of it on your mouse.
Yeah, let's see.
Double clicking?
You know, I was trying to double clicking, but it doesn't seem like it's odd. You would think if it would go back. I mean, let me know. Try escape.
Yeah, try
escape.
escape.
Escape is good. Escape's good. All right. Well, good. That was helpful.
You can also write on it. It had the little paint brush next to it.
Yeah. Let me see if I can't pull that up. Let's go to the paintbrush here. The annotate one. So it doesn't seem like I can do the laser and the writing, but maybe the writing would be better. Let's see. There's one for text. I don't know if you can see it. I could see it. Can you see that? I don't know if you can see that. There's a menu bar that comes down, and there's an eraser. I've tried this. I haven't got a lot of success with. Let me try. There's one with a shows a. Let's try that one. Oh yeah. Wow. Did you see that?
Yes.
Okay. Well, maybe this is better. I'll use this. All right. Okay. Well, thank you. That was interesting. So it's got more features than I was. Well, no surprise, more features than I was aware of. All right. Well, yeah. So that hourglass. Let's see if I can click on it with a pin. See, does it? Oh, no, it doesn't. I had to come out of that mode, I think. And how do I get out of this? Let's say I wanted to.
Probably escape again. That's
I've been trying to
probably
escape
gonna be your
here.
go-to.
Escape doesn't seem to do it for the.
Yeah, you can probably use your eraser then.
Yeah, I could use my eraser, but I'm not sure it's going to solve the problem.
Just click the pen again.
Okay. Well, the pen, right? Not the spotlight. Let's find the pen. Where is the pen? It's not the spotlight. Stamp. Oh, there it is. I think that's got to be it. Okay. All right. Now, let's see. Try this. Oh, well. I guess I'll learn.
I mean, I think if it has an eraser icon, you can like double click it and it should clear all.
Oh, really? Okay.
Yeah,
There
that's
is an
what I
eraser
think.
icon. I
Maybe.
don't see it. Well, it's selectively erasing. But I'm still trying to see. There's your magnifying glass.
Pretty sure if you hold down and just move along each one, it'll erase them.
You know, another problem I have here at home is I'm not getting the audio in. You're breaking up into.
I think he was talking about if you click and hold and then drag and put like a box around whatever you painted, you may be able to delete it all at once.
Oh. But I mean, I don't see the connection necessarily. If by marking up the page, it shouldn't be blocking me from doing other things. I don't think. I mean, as long as I can get out of it. Let me try that. Okay. That's the key. Now, they see now we're back. Okay, so that's that. I get it. Yeah. All right. Well, those are good suggestions. Thanks. I think I can use those. At least while I'm stuck here. Okay. Well, that should, I think we're about over time now. So I'll then see most of you, I think, for the 4311 class later today. Okay. I'm thinking, how do I end this meeting? Okay. So I'm ending any questions before I end the meeting? 8, 9.
No, sir.
Okay. There we go. I'm ending the meeting. All right.